Okay, let's dive in. You know how in everyday life, things seem pretty straightforward? Like
Yeah.
you see a car drive past, you can tell where it is, roughly how fast it's going. Seems
Right,
obvious.
that's our intuition, our classical worldview.
Exactly. But get this. When you zoom way, way down to the smallest scales imaginable, that certainty just evaporates. It's really weird.
It is weird. And that's where we get into the Heisenberg Uncertainty Principle. Werner Heisenberg, 1927, a huge moment in quantum physics.
Yeah, it really turned things upside down.
It forces you to question what knowing something, like position or speed, even means at that level.
Right. And that's our goal here in this deep dive, to sort of get a handle on this principle, its effects, without, drowning in the math.
Definitely. Our sources really dig into how this idea just fundamentally shifted physics.
So maybe contrast it for us. Classical physics versus this new quantum stuff.
Okay, so classical physics, think Newton, think billiard balls, cars, planets it assumes. If you know everything about a system now.
Like the exact position and speed of that car.
Precisely. Then you can predict its entire future path. Perfectly. Deterministic.
Makes sense.
But quantum physics looks at the subatomic world and says, not quite. That perfect prediction breaks down.
And that brings us right to the core of it, doesn't it? The uncertainty principle itself.
Yes. Basically, Heisenberg realized you cannot know simultaneously both the exact position and the exact momentum of a particle.
And momentum is like, it's speed and direction combined. It's oomph.
Yeah, mass times velocity, how much it's moving and where. The more precisely you pin down its location.
The less precisely you can know its momentum. Its speed and direction become fuzzier.
And vice versa. Focus on its momentum and its position gets blurry. It's a trade-off.
Like trying to perfectly photograph a speeding bullet, you get a clear image or you know its exact speed at that instant, but maybe not both with infinite precision. Is that close?
Sort of, but the analogy breaks down because the key thing here is it's not our fault.
Ah, right. You mean it's not just that our measuring devices aren't good enough?
Exactly. It's not a technological limitation. It's fundamental.
Yeah.
It's baked into the fabric of reality at the quantum scale. Nature itself imposes this limit.
Wow. So particles don't have a precise position and momentum before we measure.
Well, that's where it gets really philosophical.
Huh.
But operationally, they exist in a state of probabilities, like a cloud of possibilities.
Maybe here, maybe there kind of situation.
Kind of. A range of potential positions, a range of potential momentums. It's only when you measure one.
That it sort of snaps into a more definite state for that property, but the other one becomes less definite.
That's the essence of it, which
Yeah.
is, as you said, totally counterintuitive to us macroscopic beings.
Yeah, my desk feels pretty solid, Definitely here.
Right. We're used to definite properties. But countless experiments confirm this quantum uncertainty. It's real, even if it feels bizarre, like quantum tunneling.
Where particles pass through barriers they shouldn't have the energy to cross.
Exactly. That happens because their position isn't perfectly defined. There's a tiny probability they can just appear on the other side.
Okay, so it's not just some abstract idea. It has real consequences.
Huge ones. It's why atoms are stable. If an electron could have a perfectly defined position and zero momentum, it would just spiral into the nucleus, right?
Oh, I see, but because of the uncertainty.
If you tried to confine it too precisely near the nucleus, its momentum uncertainty would become huge, meaning it could have a very high speed, preventing it from just sitting there. It maintains its sort of energetic balance.
So this uncertainty principle is actually what holds matter together. That's fundamental.
It really is. And it goes beyond just atomic stability. Think modern technology.
Like what?
Well, semiconductor physics, how transistors work in your computer, relies on quantum principles. Quantum computing and cryptography directly harness these weird effects, including uncertainty.
Okay, so it's not just theory, it's engineering too. Now, you touched on observation playing a role. Does the act of measuring change things?
That's one of the deep questions. In quantum mechanics, measurement isn't passive. To measure a particle's position, you have to interact with it, maybe bounce a photon off it.
And that interaction inevitably disturbs its momentum, right?
Precisely. So some interpretations emphasize this disturbance aspect. Others focus more on the inherent probabilistic nature before measurement. The maths works regardless, but the philosophical interpretation, that's still debated.
Fascinating. So the big takeaway is, down at the quantum level, the universe plays by different rules.
Very different rules. Rules that include inherent limits on what can be known simultaneously.
Nature keeps some secrets, or at least presents them probabilistically.
You could say that? The Heisenberg Uncertainty Principle is a stark reminder of the strangeness and wonder of the quantum world.
Okay, so here's something to chew on. If there are these fundamental limits to knowledge at the very smallest scales of reality, does that idea echo anywhere else? Are there other areas, maybe in complex systems or even in understanding ourselves, where inherent uncertainty might be a feature, not a bug, something we need to accept or approach differently?
That's a really provocative thought to end on. Something for you all to ponder.